Hi everyone, it's Adam again. So today is going to be the very last video on statistics before I move on to geometry and trigonometry and stuff like this. So today I'm just going to give a quick recap of, just in case, you didn't watch my last video, which could very well be a possibility. So basically, we have this thing called a normal distribution, where in the center we have the average, which is mu. Then typically we go sigma to the right and left, which could be this distance, where sigma is just the standard deviation. Okay, so mu is just the mean or the average. Sigma is just your standard. Your standard deviation, okay? So basically, it's just kind of sigma just tells you how spread out your data is. So if I tell you, okay, the mean heights in Ireland is 5'8", if I told you the standard deviation was a foot, then that means that it would be a possibility that you'd find it's a relatively common thing that you'll find someone who's 4 foot tall and someone who's 8 foot tall. That doesn't happen. So heights are quite narrow or quite it's like you'd expect to, if you went around your school or whatever and you measured all the heights of your male teachers, you'd expect that the shortest might be, maybe 5'2", 5'3", 5'4", and the tallest might be 6'5", So it's like they're not actually spread out that much. Okay, so sigma is just a measure of how spread out is your data. Okay, that's all. Now, this is for a population. And for a population, it's like for the whole population of Ireland, if they did a census in Ireland and they got the population and they knew exactly what the mean was and exactly what the standard deviation was, then they could say that a z-score is equal to x minus mu over sigma. So remember, a z-score is basically just how likely or how unlikely are you to get a result of x. Okay, so x is basically what you're testing. Okay, so if I wanted to see, okay, how common is the height 6'5" in Ireland, you would say x is equal to 6'5", your mu is your mean, which would be 5'10", and then your standard deviation sigma would be maybe 2 or 3 inches. You plug all those numbers in, you get a z value of maybe 2 or 2.5, and then you'll see, okay, that's quite uncommon. That's all a z-score is. It's just how common or uncommon is the possibility of getting this x. Okay, that's all. So also, if you look at the formula, you might say, okay, why is it divided by sigma? Basically, what you're asking is like, how many standard deviations are you away from the mean? That's basically what a z-score is. A z-score, if it's 2, it just means you're 2 standard deviations away from the mean. If it's -2, you're 2 standard deviations left of the mean, so below. That's all a z-score is. It's how many standard deviations are you away from the mean. Okay? So that's why you need to divide the x minus mu by sigma, because it's just, you're dividing the sigma in there. Because obviously, if I said, this is just for example, if I said, here you are, this is the mean, which is 130, this is 160, and the standard deviation is 15, and I asked you, okay, well, how many standard deviations are you away? You'd say 2, because this distance here is 30, which is 2 times sigma. So this would be 2 standard deviations away. Okay, so that's what a z-score actually is. It's just how many standard deviations are you away from the mean. Now, this is all grand, and it's for a population, okay? Which is very important. So it's for a population. Now, if we're doing a sample, so let's say we only do a sample of a population. So let's say the population in Ireland, it says that the average height of a male in Ireland is 5'10". Grand. Then if I want to do a sample, I might go around my school and, measure the heights of my teachers and basically just see, okay, well, what is the average of my teachers? And maybe it's 5'8". And then what you're asking is you're saying, well, how unlikely is that value? Okay. So basically, your z-score in this case, so again, your z-score is just how unlikely is that value. So if I measure my, your teachers being a 5'8", what's the chances that you actually get that? It's the same thing, only that now your standard deviation changes. Okay, so if you're working with a population, this is the formula you will use. Okay, so I'll do, I'll do questions in a while, but basically this is just kind of what you're doing. So it's just, if you're working with a population, it's going to be the z-score up here. If you're working with a sample, this is the z-score. Okay, and just for clarity, if you plugged in n equals 1, you get x minus mu over sigma, which is exactly what you get up here. Okay, so remember, this is for a population. If you're saying, okay, how likely is it that I will get this value for one person? It's this. Now what you're saying is, what's the chances that I will get this value for a sample? Now you're dividing it by root n. Okay, that's the only difference. Okay, so that's what you're doing here. All right, so I think the easiest thing to do is to do a question. Now, if you know these formulas, then it's one of those things of, if you're in an exam, it's typically quite obvious as to what one you should use. If they tell you that there's 70 people in a sample, then obviously you use this. If they give you what n is, so n is just how many people are in the sample. So if they give you that, then it's quite obvious that you should use it, okay? So hopefully it'll be a little bit more simple now in a second once I do an example of a question. So here it says, a car battery manufacturer claims that the distribution of the lengths of life of its premium battery has a mean of 54 months. So the mean that we're being told is 54 months. This is what they're saying. And remember, this is a mean of 54 months for the population. Okay? So it's a mean of 54 months for the population. Grand. And a standard deviation of 6. So sigma is equal to 6. Grand. A consumer magazine tests a random sample of 50 batteries. Okay, so n is 50. So you're testing 50 of them. Grand. To investigate the company's claim. So first of all, it says, so sketch the sampling distribution. So that's just simply, they're looking for the normal distribution, where this is 54, this is going to be 60, this is 48. And then if we want to do it again for the sample, you do the same thing. But now, so here your sigma is just equal to sigma, grand. But now your sigma is of the sample. So now this is going to be sigma over root n, which is 6 over root 50, which is approximately equal to 0.85. So we just have a different standard deviation now. So that's the main thing with these, guys. So again, please don't get too bogged down. You're just saying that the standard deviation should be smaller, because it's like if you're getting the average of heights of people. If I said, okay, so I'm going to go around and I'm going to look for, and I told you to look for one person who was 6'5". So 6'5" is a very unlikely result. Okay, that's fine. But basically, actually no, sorry, but I'll just write in what these are. So remember, these lines correspond to the same thing. So this line and this line correspond to the same thing. This line and this line correspond to the same thing. Okay. This now because you do I did minus 6 and plus 6. Now I'm going to do minus 0.85 and plus 0.85. So it's 53.15 and 54.85. So basically what this is asking, it's saying, okay, go around and find me a battery. So this is, again, remember, this height of the graph is just telling you how likely it is. So this is saying, if you're looking for one battery that has 60, that's the same probability as finding 50 batteries that have an average of 54.85. Okay, so hopefully that makes sense, that basically if I told you to go out and again find someone that's 6'5", it might take you however long. If I told you, okay, go off and find 50 people who are 6'5", or 50 people who have an average height of 6'5". So if you find one person who's 6 foot, you need to find someone who's 6'7" or 6'8" to, average out at 6'5". And I told you to do that. That's a much harder task, because obviously it's like you have to find tons of people who are around 6'5". It becomes very unlikely. That's what this root n here is doing. It's telling you that the more you look at, the less likely that result is. That's why up here, it's saying, so whatever chance it is, it's basically telling you that it's kind of likely, but it's not very likely. It can happen, but it's not totally likely. Here, it's basically saying that it's now 54.85. So if you looked at 50 batteries, there's basically the same chance that you'll get an average 54.85 as you would of finding one of them that has a 60. Okay? So hopefully that makes sense, that the more you sample, the less likely you are to get a very different result from the mean. Okay, so hopefully that makes sense, that if I looked at one person, it's the same thing with the probability when we were saying if flipping a coin. If you flip a coin 3 times, you're obviously going to get like 67% heads or 67% tails. But if you did it 100 times, you'd expect it to be roughly 50-50. It's the more times you do it, you're less likely to get a really kind of weird or unbalanced answer. This is what the sigma over root n basically symbolizes. It says that if n is bigger, if I plugged in 100, all of a sudden I'm getting 0.6. So if I did 100 of them, it's even less likely. If I did 1,000 of them, it'd be way less likely. 10,000, it's, and so on and so on. So that's all this is saying. Okay? So hopefully that makes sense, that obviously the more you test, the less likely it is, and therefore your standard deviation has to change, because it will become less likely. Okay. The next one, it says, assuming that the company's claim is true, what is the probability that the magazine's sample has a mean life of 52 months or less? So I want to know, what is the chance that I will find a result of 52 months or less? So basically, what's the area under the graph here? So again, I want to get a z-score. So z is equal to x minus mu over sigma over root n. Remember, x is what you're testing. So I want to see what's the chance of me getting 52 over 6 over root 50. This is roughly equal to minus 2.36. Okay. Oh, sorry. Actually, can I do pictures? No, I cannot. Okay, yeah, I can. All right, there we go. Okay, sorry, that was very unprofessional. Okay, so basically, now we have our Z tables here. Sorry, I might just move them just because that's kind of annoying me. Okay, so we have a Z equals minus 2.36. So basically what I want to do is I want to say, okay, grand, so where's 2.36 on this? So remember, if you're looking for a minus Z value, you always just look for the positive. So minus 2.36. So first of all, 2.3 is here. And then 0.6 is over here. So I need this one here. So the chances of getting that are going to be 0.9909. So now that means that there's a 99.9% chance that I will get more than it. So this is your 99.09% chance that I'll go there. Okay? So this chance here is just going to be 1 minus that. Okay? So it's 100 minus 99.09. So it's going to be 0.91%. So there's a 0.91% chance that you would get that. Okay? And then finally it says, if the magazine's sample had a mean life 52 months and you were the journalist of the magazine reporting for the company's claim, what would you conclude regarding the claim? You would say that it's very unlikely. You're saying that it's unlikely that the true mean is 54. Because if the true mean, so again, sorry. What you're testing with this is you're basically saying, is the mean actually equal to 54? Because they say it is. Of course they're going to say it is. If it was 53 months or 53.5 months, of course they're going to say it's 54 months. Okay, because obviously they want it to sound like their product is very good. But it mightn't be. Same thing with, like a Mars bar or something. I might say, oh, the calories are 130, but it mightn't be. It might be 132 or 133. They're trying to make it sound better. Because 130 sounds better than 133 or 134. So that's why you do these tests. And you say, okay, you say it's 54. I'm going to test it. So you test as many as you can. So you want n to be as big as you can. Here they did 50. So 50 is fairly good. To be honest, that's quite a large amount. Obviously, the more the better. But, as long as you don't test like 2 or 3, if you test 10, that's probably good enough. But they did 50, so that's quite good. So they did 50 and they got that. Okay, we tested 50. There was an average. You plug it into your Z-score. You see what the chance of that happening is. And you get that it's less than 1%. And then you say, well, it's less than 1%, so that's fairly unlikely. So it's unlikely that their claim that it's 54 months is true. Okay? All right. So I might do one more of them. And then maybe I might just leave it at that. For these ones anyways. No, I think I might just leave that. To be honest, I think that's covered everything that I wanted to cover. Yeah, I think that's kind of everything that I wanted to cover. Okay, so the next one I want to do is basically so a confidence interval. Okay. So confidence intervals. So basically the whole thing that you do, so typically you do a 95% confidence interval. Okay. Okay, so that's typically what goes on. All right, so the whole idea is you say, okay, I want to do a 95% confidence interval, which basically means I want to be able to get an interval, which is obviously to do with the mean, that I can say, okay, I am 95% confident that if you go off and you test a random one of our products, it will fall within this range. Okay? So that's basically what this is. It's just saying you can say with 95% confidence that the answer that you're going to get from a sample is basically going to be between sorry, I should probably put X. So whatever you get, which is X, so that's what you're getting, it's going to be mu plus some interval, or it's going to be mu minus some interval. So it's just that you can guarantee it's within this interval. Okay? That's all. So you're just saying that I can say with 95% confidence that if you do this, you will get an answer that's in this interval. Okay, now what is this E? E is always equal to 1.96 sigma, or 1.96 sigma over root n. So this is just if you're doing for a population. This would then be if you're doing it for a sample. That's all. Okay, so it's just saying that if you grab the mean and go plus or minus this 1.96 sigma over root n, you will get that it's going to be that it should be within this this interval. Okay. Now, you might be saying, okay, where has this 1.96 come from? That makes no sense. The 1.96 is actually what gives you the 95%. Okay? So I'll just explain it once. It's not that important to know. Sorry. It's very important that you know it's 1.96 gives you 95%, but it's not like you're going to be asked to prove it. Okay? So as long as you know 1.96, 95%, you're grand. The way you do it is, if I come in here, and let's go to 1.96. So where is 1.96? It is here. You will notice that's 97.5%. So 1.96 gives you will give you that this is going to be 2.5%. So if it's 97.5 is left, then only 2.5% is to the right. The same thing with minus 1.96, that will give you 2.5% here. So basically, if you go to the mean, which is here, and you go left and right, 1.96 sigma, then you have to have 95% of the data encapsulated in here. Okay, so that's why it's 1.96. All right. Okay, so I'll do a question now, and then we'll see how this goes. So it says a random sample of 400 apples. So again, you're using a sample, and they told you the n is 400. They will never tell you how much is in a population. Okay, that's another thing. So if they tell you, oh, there's 400 in a sample, that means it's the root 400. If it's a population, typically they'll never tell you what the number is. Okay, so if you don't know, is it a population or a sample, or if they don't say it, but they give you a number, then chances are it's going to be the sample. So it's 400, that's great. And then it says, was taken from a large contingent with unknown mean. Okay, so they don't know what the mean is. So basically they've gone to this place, they've gotten 400 random apples, and they want to give what's the best average that you can give them. That you can say, okay, the actual mean is between this. Okay? And it says the standard deviation is 15 grams. And it says that the mean weight of the sample is 85.6. So that's the sample, okay? So now they're saying, okay, construct a 95% confidence interval for the mean weight of the apples. So a 95% confidence is just you say, okay, so I know it's going to be between 85.6 grams plus, remember it's 1.96 sigma over root n, and it's 85.6 minus. Okay, so you can say this comes out to 84.13, 87.07 grams. So you can say with 95% confidence that the average of the population of the apples is within this range. Because obviously, they could have 1 million apples. You're not going to measure all 1 million of them. You know, that's too much time. You'll just say, listen, you know, let me test 400. Let's say it's this. So we can say that our mean should be roughly between these, okay? All right. So that's That's that. Okay. So I might just do maybe one more. Okay. Yeah, I'll just do one more, and I think I might leave that at that then. So it is a random sample of 40 women. So again, sample, you're told N is 40. Grand. Was selected from the population and their pulse rates measured. The mean pulse rate of the sample was, so mu for the sample is 76.3. Assume that sigma, the population standard deviation, is known to be 12.5. So you're told that the sigma of the population is 12.5. Great. Construct a 95% confidence interval for mu. So the average, mu, is again going to be less than or equal to 76.3 plus 1.96 sigma over root n. Okay, plug that into your calculator, you get 72.43. Okay, and that's it. Okay, that's all you have to do. So again, this is the mean of the population. Okay, and yeah, that's kind of it. So as long as you know that it's 1.96, you're flying. And not much work to be done with it, okay? All right, so the next thing I want to do is estimating a population proportion. So the population proportion, basically, this is now you'd use when it's when you say, okay, so so let's say you did a sample of voting in your school or whatever, and you said, okay, well, 20% of people voted for Sinn Féin and 80% of people voted for Fianna Fáil. Grand. You'd say, okay, well, what's that then for the population? Then you want to say, okay, I want to create a 95% confidence interval, basically saying, okay, that I can say that the actual percentages are going to be between this and this for the actual election. So, it happens over in America a good bit, and they do kind of mock polls, and they say, what do people want to vote for? And then they do a 95% confidence interval based on that, which technically isn't correct because obviously that's going to be biased. If you're watching a conservative TV show and you're surveying conservatives, then of course they're probably going to vote conservatives. So it's one of those things, you also want your sample to be unbiased, which is a very difficult thing to do. Okay, so it's a population proportion. So it's just a percentage or a fraction. So P is the population proportion. P hat is basically the sample. So it's basically just how many voted for or how many did it over the total amount. Grand. And that's it. And so sigma in this case is the square root of P1 minus P all over N. Like this. Okay? So now all of a sudden E is just going to be 1.96 sigma P hat. So, sorry, that kind of just looks a little bit weird. Sigma. So now, this is basically just how you're calculating this. So it used to be sigma over root n we were calculating. Now we're just calculating this thing instead. Okay? So let's do an example. So it says, in a survey of N voters, so we're not told how many voters there are, 0.7 of the sample said they voted in a recent referendum. A 95% confidence interval of the proportion of voters who said they voted in the referendum is given by this. Okay? It says how many voters were surveyed. So basically what you have is, you have that it's p hat minus e is less than or equal to p is less than or equal to p plus e. Okay? So remember, p hat is equal to 0.7. So I can just work with this one and say, well, I know that 0.7 plus e is equal to 0.7284. So e is going to be 0.0284. And e is equal to this thing up here. So e is going to be 1.96. The square root of p 1 minus p over n. That's equal to 1.96 square root. P is 0.7. 1 minus p is 0.3. N we simply don't know. Okay? Divide both sides by 1.96. I'm going to get that the square root of 0.21 over n is equal to 0.01449. I can now square both sides and get 0.21 over n is equal to 0.000209954. So n is going to be, it's going to be 0.21 over 0.000209954. So n is going to be equal to 1000. And this is just rounded to the nearest number. Okay? So that's just very, very important that obviously n is the number of people in the sample, so obviously round it. Okay? Don't leave it as 999.7 or something like that, okay? So just always round it. Okay. The next one says, if the margin of error for a 90% confidence interval, so before it was 95, now they're changing it to 90. So they're saying if the margin of error, E, for a 90% confidence interval is equal to 1.645. So just remember, the only thing that's changing is the number in front. If I wanted a 95% confidence interval, it's a 1.96. Now it's a 90%, so it's 1.645, okay? So then this is going to be the square root p hat 1 minus p hat all over n. Construct a 90% confidence interval for the proportion of voters who said they voted in the referendum. So in this one, you have, again, your p hat is going to be your 0.7. And n is going to be 1000. So E90, if you plug all those numbers in, you're going to get this. So I end up that P is going to be less than or equal to, it's going to be 0.7 plus E, and then 0.7 minus E. And then if you plug this in, you're going to get 0.6762 is less than or equal to P less than or equal to 0.7238. Okay? All right. Now, just before I go any further. So this is the confidence interval down here for a 90%. Sorry, I'm just really bad at this. And then this is the confidence interval for 95%. What do you notice with the numbers? Is the interval wider or smaller? This interval is smaller. Why? The reason is because down here we're only 90% confident that P is between this number and this number. But if I make this interval bigger, as it is up here, then I can be more sure that P is going to be within this interval, and that's where the 95% comes from. Okay, so just be careful with that. That's typically how it's going to go. All right? Okay. So that's it. All right? Okay, perfect. So that's the end of that question. So I will finish this kind of part of the chapter with one more. And then, yeah. Okay. All right, so perfect. So this is one thing that, this is like a formula that I'm going to derive. I'll just leave it the way it is, okay? So it just says that you have a 95% confidence interval, E, is 1.96, the square root of P into 1 minus P, all over N. Now, what they want to know is they want you to maximize this, this function, okay? So if you haven't done derivatives yet, just take me at my word for it. You want this to be as big as you can. So what P will give you the biggest E? So basically, what I can say is I want to make P into 1 minus P as big as possible. So I want to make P minus P squared as big as possible. So what I want to do is I want to differentiate. So if I differentiate with respect to P, I'm going to get 1 minus 2P, and I equal that to 0. I find that P equals a half will maximize this. So the biggest this can be is a half minus a quarter, so it's a quarter. So that's the biggest that can be, okay? So the biggest E, so E max, is equal to 1.96, the square root, 1 over 4, all over N, which is 1.96 times a half. The square root of a quarter is just a half. So it's 0.98 over root N. So this is the biggest margin of error you can get, okay? Now, this is usually approximated by this. This is a very important formula, okay? I don't think it's in the log tables either, all right? So just to give note to it, this was the original formula that was introduced into the maths paper. It was used for a couple of years. This formula is quite a bad approximation, so they kind of stopped asking it for a while, but it's gotten trendy in the last 4 or 5 years, okay? So it's one of those things that if you were only given, so this is called the margin of error. If they say, what is the margin of error for the population? So basically the margin of error is just asking for what's the biggest amount of error we can have. This is what they're talking about, okay? 1 over root n. So the biggest margin of error for a population of 400 is 1 over root 400. That's 1 over 20. That's 5%, okay? So the biggest uncertainty you can have, so if I survey 400 people and 40% of them say something, I can say with 95% confidence, so probably more confidence, but at least 95% confidence that it's within 5%, either side, okay? So if they ask you for the margin of error, or they give you no numbers in the question, in the leaving cert, and the only thing they give you is the number of people in the sample, it is 1 over the square root of n, okay? You just have to know it. If you don't know it, there's nothing you can do about it, okay? You're just kind of caught, all right? Okay, so that's just a thing to know. All right, the next thing that I want to do hypothesis testing, okay? So hypothesis testing is basically all you're kind of doing is you're just how can I put it? It's like earlier on we had the car batteries and we said, oh, it was quite unlikely. So back up here. And we said that there was a less than 1% chance. Actually, sorry, what time did I start this video at? Okay, I've been going for an hour. I might just finish this. It'll probably take me 15 more minutes and then I'll just have one big section on it, and that's that. Okay, so basically when it comes to hypothesis testing, what you're doing is, so back about the batteries, when it was like less than 1% chance that this would happen, there's a thing you can do and you can test it. You can say, okay, I don't think that the actual mean is 54. Okay, so you're testing it. So it's like quality control. It's they basically go into a company and the company might claim, okay, our products are especially like if you'd ever see like some weight loss calorie chocolate bar or something, they might say, okay, or protein bars, say, okay, there's this amount of protein or there's this amount of calories or whatever. Basically, teams will go in and they will test maybe 1,000 of them and say, okay, we will make a 95% confidence interval and we will be able to tell you and say, okay, we reject your claim that, you have 30 grams of protein in this bar. We think you have less. Or they will say, this is a very important language. They will say, we fail to reject your claim. So you never say you accept it, you just say you fail to reject it. Okay? So either you reject or you fail to reject. So you never accept. Okay? Just be careful with that. Okay. So here then it says, it is thought that 30% of a certain kind of apple seed will germinate. In an experiment, 85 out of 300 seeds germinated. What conclusion can be reached at 95% confidence level about the true population proportion of seeds will germinate? So first of all, your hypothesis. So you have your null hypothesis, which is H naught. So H naught is basically what you think is, you just have to say what's going to happen. So the null hypothesis is just, so what are we testing? We're testing that, because it says it's thought that 30% of a certain kind of apple. So it's saying that is 30%. So that's the null hypothesis. The null hypothesis, you're saying, okay, we think it's 30%. The alternative hypothesis, which is H1 or HA, is just P not equal to 0.3. That's all. Okay? So basically, your alternative hypothesis is just the opposite of what you said for your null hypothesis. Okay, so your null hypothesis, like your baseline, like what are we testing? We're testing, is the probability actually 0.3? So the next thing, what I want to do, I want to calculate the sample proportion. So what's p hat? So p hat is going to be, they said 85 out of 300. So it's just going to be 17 out of 60. Grand. Now I want to do a 95% confidence interval. So that's 1.96 square root. It's p hat 1 minus p hat all over n. So 1.96, the square root, 17 over 60, multiplied by 43 over 60, all divided by 300. Okay? So I can say with 95% confidence that the actual p is within this interval. Okay? If you plug these in, so remember p is equal to 0.3 and then e is equal to this thing, so just plug that into your calculator, you will find that it's 0.232. Okay? So we have this. So p is within this interval and we can be 95% sure. So initially we said that p is 0.3. Do we have enough evidence to say that p is not 0.3? No, we don't, because p is within this interval. And therefore we say we fail to reject the null hypothesis. So that's that. Okay? All right. So that's all right. So now the very last thing that I want to do is calculating a p-value. Okay? So and don't worry, this video is about to end very, very soon. So this is the very, very last one, okay, on statistics. All right. So the worked example. So it says the mean systolic blood pressure for adult males aged 30 to 45 is 128. Airport authorities in the UK are concerned about the effects of stress on their male air traffic controllers. A random sample of 100 male. So first of all, N is 100. Sample of 100, grand. Traffic controllers in this age group is selected. Their mean blood pressure is 132. So the mean of the sample is 132. And their standard deviation is 15. Okay? Construct a 95% confidence interval for the mean blood pressure for the air traffic controllers. Interpret this interval. So basically, what you do is you say, okay, well, the mean is 132. You're going to minus 1.96 sigma over root n. That has to be the actual mean. And then 132 plus 1.96 sigma over root n. Okay? So, it's simply equal to 132 minus 1.96. 15 over root 100 is 15 over 10, so 1.5. So we end up with okay. So this is our 95% confidence interval. And sorry, another thing to just note is sometimes they will say at 5% level of significance. 5% level of significance is the same thing as 95% confidence. Okay? So level of significance, 95% confidence, same thing. Okay? So just in case they say that in the leaving cert, because they could. All right. So that's that. So basically it says interpret this interval. So we can say, well, they said that the mean for the population is equal to 128. 128 is not in our interval. Okay? So it's not in the interval. So we can say that this is quite, okay, so it's a significant result. We didn't expect to get this interval. You would have expected that it shouldn't make any difference, but because their blood pressure is higher, that would then you would say, okay, well, that obviously means that it's going to be quite a stressful job. Okay, and that's the cause of their blood pressure being higher. Okay. All right, then it says carry out an hypothesis test at 5% level of significance to find out if there is evidence to suggest that the mean blood pressure for male air traffic controllers in the UK aged 30 to 45 is different to the global average. So here, I want to create a z-score. So my z-score is going to be x minus mu all over sigma over root n. So exactly what we've been doing. 132 minus 128 all over 15 over root 100. This is 2.67. Okay? So, again, your z-score, you always look at it and you say, okay, this would be 0. Here we have a score of 2.67. This is 1.96. This is minus 1.96. So basically, where are the regions where we will say it's a significant result? Anything here. So anything within 95% would be an insignificant result. Anything outside of the 95%. So remember, this gives you 95% in here. 2.5% here, and 2.5% here. Okay, so this is a very significant result because it's greater than 1.96. Okay. All right. So, I was supposed to do a null hypothesis. Sorry. So my null hypothesis H naught is that your average is still equal to 128. And my alternative hypothesis is that my average is not equal to 128. So that's all. I'm just saying that the null hypothesis is basically saying that the blood pressure is still 128. I tested that. I got this result, which is way bigger than 1.96. So it's a significant result. And therefore we can say we reject the null hypothesis. Okay. Very last one. It says, give a p-value for this hypothesis test and interpret this p-value. So the p-value is basically, it's just the probability. So a p-value is just the probability of getting this z. Okay. So the p-value is specifically, what's the chances of getting a z-score stronger than this one? So greater. If this was minus 2.6, then I'd be saying less than. Okay, so it's just what's the chances of being even further from the mean than this one. Okay, so what you do is you'd say, okay, well, what's my z-score? That's 2.67. Basically, what I want to do is I want to say, okay, so this now, if I plug it in and 2.67, so if we go back up here, okay, 2.67. So 2.6 is here, 7 is here, so it's this one, 0.9962. So the chances of getting the red region is going to be 1 minus 0.9962, which is going to be 0.0038. Okay? Now, your p-value is always equal to the probability that the magnitude of z is greater than or equal to the magnitude of your z value, which is 2.67. So basically, you always have to multiply this by 2 because you're always looking for this as well. Okay, so you want to know what's the chances of getting an even stronger result than 2.67. So you want your magnitude of z to be greater than this. So you get this value, say that there's a 0.38% chance of being bigger, and therefore there's a 0.38 chance of being smaller as well. So you multiply it by 2, and you get 0.0076. So my p-value is 0.0076. Okay, so the chances of getting a stronger result than this is basically 0.76%. The significance value is 95%, which is the same thing as 0.05. So your p-value is less than 0.05, and therefore we reject. That mu is equal to 128. So basically, if your p-value is lower than 0.05, you reject it. If p, so big if p was greater than 0.05, then you'd say we fail to reject H naught. Okay, so that's how you do p-value. So p-value is the probability that you'll get a z value even more obscure or unlikely than this one. Okay. All right. Okay, I think that's it for statistics. The very next thing is to go over some geometry. So yeah, I think I'll leave it there for today. Thank you very much for paying attention. And if you got through this video, it's it was a very long one. So thank you very much for paying attention. And yeah, I'll see you in the next video. Bye.